Good morning and welcome to the first tutorial in ENEL 573. This is the one that's going to focus on the material in assignment 1, and I'm going to base what I'm going to talk to you about this morning, or at least it's morning for me, on the feedback that you guys provided in the online quiz on D to L. And thank you again for everybody who filled that out. There can be no question that one of the most common comments on the feedback form was, just reviewing this tutorial material. It's like people found that there was a lot of material to review and they were a little rusty on the probability. A few people, or one person anyways, commented that they didn't feel the assignment was very closely tied to the lecture material. And all of these things are absolutely true. So this assignment is more intended to get you to review the ENEL 419 material than it is to reinforce what we've been talking about in the lectures so far. From assignment 2 onward, you're going to find that the assignments are much more closely tied to the lecture material. However, this first one is really meant for a review. I mean, these questions are 573-ish. We're talking about retransmissions, we're talking about error detection, but they can all be solved using the fundamentals from ENEL 419. All right, so let's start with question 1. A. So question 1A asks, in a 4-bit frame, write an expression in terms of p, and little p is the probability of bit error. Write an expression in terms of p for the probability that the first and last bits in our 4-bit frame are good, and the middle 2 bits are bad. So little p is equal to the probability of bit error. And I find it's helpful to, there was one student who said translating from words into probability is tricky, and it absolutely is. I mean, I would say that's probably the trickiest part, or one of the trickiest parts of working with probability. But I always find it helpful to sort of look for keywords. And so if I'm asking you to determine the probability of something, look for keywords, and in this case, it's write an expression in terms of p for the probability that the first and last bits are good and the middle 2 bits are bad. And so when you hear that word "and," then it sort of suggests intersection. And so what I'm going to do is I'm going to write out a probability equation, but something that's still mostly in terms of words, right? So we want to find the probability that the first bit is good and the second bit is bad. So rather than writing the word "and," I'm going to put in the little intersection term. Second bit bad and third bit bad and fourth bit good. So whenever you have the word "and," so whenever you're trying to figure out the probability of, let's say, A and B, we can write this probability in terms of the probability of A by itself multiplied by the probability of B, as long as those two events are independent. And in this question, I tell you that the bit errors are independent. And so as soon as you hear that word "independent," you know that you can use this equation here. And so our probability expression with all of these ands in it can be written as probability of the first bit being good multiplied by the probability that the second is bad, multiplied by the probability that the third is bad, multiplied by the probability that the fourth is good. If the probability of a bit error is p, The probability that a bit is bad, therefore, is equal to P. And the probability that it's good is 1 minus P. So we can write this expression then in terms of the variable little p. So the probability that the first bit is good is equal to 1 minus p. The probability that the second is bad, the third is bad, is equal to p, and then the probability the fourth is good is equal to 1 minus p. And that's it. So the whole purpose of part A is to get you thinking about how we can translate this notion of, a bit being good and bad and bad and good to basically the product of a bunch of terms that are equal to basically p or 1 minus p. Okay, so question A was meant as kind of a warm-up because I gave you sort of a specific scenario. Part B now asks you to determine sort of the general expression. So for part B, the length of our frame is now equal to capital N bits, and the number of bit errors is equal to k. And basically what we're asking for here is an expression for the probability of k errors in an n-bit frame. So up here, if we go back to question A, or maybe I'll write it down here. So in part A, we basically asked the question, what's the probability that we have 2 errors in a 4-bit frame? And so looking at this expression up here, we can say, well, if we have 2 bad bits, that means we have to have 2 p terms in our product, and the rest of the bits are good, so the rest of the bits correspond to 1 minus p terms. And so we could say, well, the bad bits are represented by p raised to an exponent equal to however many errors there are, right? In this case, there were 2, so we had 2 p terms. And then 1 minus p is just the represents all the bits that are good, and then the exponent up here is just the number of bits that are good. And so we could say, all right, if we put this aside, then our other expression up here could be equal to p to the k, right? So we've got k bad bits, and so p represents the number of bits that are in error, or sorry, p represents the bad bits and k represents how many p terms we have. And then if we have k bad bits, all the other ones must be good, and so we have 1 minus p raised to the power of n minus k. And we might be tempted to stop there, but we have to add one more piece of information. In question 1a, I gave you a specific pattern. I said specifically, the first bit is good, second bad, third bad, fourth good. However, what we're asking down here is just in general, what's the probability that k bits can be bad in an n-bit frame? And so the expression that I have in this box here is not quite correct, because there are several different ways we could have 2 bad bits in our frame. And so if we just draw this over here, up here in part A, I asked you for the situation where we had first bit good, second bit bad, third bit bad, fourth bit good. However, we could have also had 2 bad bits followed by 2 good bits. We could have had a bad bit, 2 good bits, and a bad bit. Or we could have had 2 good bits, 2 bad bits, and so on. So there is a whole bunch of different combinations that will give us 2 bad bits in our frame. And the word combination is a hint that we have to use the combination formula to figure out how many of these terms that there are. And so the probability that we have this combination is just equal to, actually I'm running out of space, so I'm going to move this down. So the probability we have a good bit, 2 bad bits, and a good bit is equal to 1 minus p, 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 1 minus p, or in other words, p squared, 1 minus p squared. The probability of having 2 bad bits and 2 good bits is equal to p times 1 minus p times 1 minus p, which is equal to p squared times 1 minus p squared, right? So I mean, these two terms are the same, even though the order of the bits are different. And so basically the probability of 2 bad bits occurring in our 4-bit frame is always going to be the same. Like each one of these terms have the same probability expression. We just have to figure out how many terms there are and then multiply this expression by that number. And the number of combinations is just given by the combination formula. And so the overall expression, the probability of k errors in an n-bit frame is equal to nk, or the combination formula, p to the k, 1 minus p to the n minus k. All right, so now for part C of question 1. Part C says a frame error occurs when 1 or more bits are bad anywhere in a frame. And you didn't need to know this to solve the question, but we understand now from the lectures that the reason why a frame error occurs if 1 or more bits are bad anywhere in the frame is because the error detection scheme we're using, whatever scheme it is, parity bit, internet, checksum, or CRC, any error detection scheme will indicate an error if 1 or more bits are bad in the frame. And then we have to throw the whole frame away, and because we don't know exactly which bits are bad in the frame. And so determining the probability of frame error is really important, and it's an expression that we're going to be using quite a bit in the class. So, so a frame error occurs if we have 1 bit bad, or 2 bits bad, or 3 bits bad, or 4 bits bad. So, or, you know, all the way up to n bits. And so one way to solve this question is we start at 1 bit bad. So the probability of 1 bit bad, or 2 bits bad, or all the way up to n bits bad. And so because these events are mutually exclusive, you can't have exactly 1 bit bad and at the same time have exactly 2 bits bad. Because we see the word or here, and because these events can't happen at the same time, we can add their individual probabilities. And that's one way to solve this question. The problem is then you get this kind of, you get a summation, which maybe we don't really want to work with. And, you know, n, in our examples, n is usually a pretty small number, but in reality, n could be, you know, thousands, equal to thousands of bits. And so I'd like to find a slightly simpler expression for this. And so the probability of one or more bad bits in the frame is actually equal to 1 minus the probability all bits are good. And this probability is just equal to the probability that bit 1 is good and 2 is good, all the way up to n being good, which is just equal to 1 minus p times 1 minus p, all the way up to 1 minus p for bit n, which is just equal to 1 minus p to the n. So the probability of a frame error is equal to 1 minus p to the n. So nice and small, easy to work with. If you did it the other way, that's totally correct. And even on an exam where I'm marking things correct or incorrect, obviously, I would give you marks for that, but this is just quicker and a little bit more elegant. I'm not going to bother doing part D of question 1 because it's just plugging values into the formulas. Part E is where you have, so for part E, you know the probability of frame error, and you know, so you know this value, you know the value of P, and you have to solve for the value of n. At least one person said they weren't sure how to do that. Basically what you do is you group the equation 1 minus p to the n equals 1 minus probability of frame error. Then you take the log of both sides. Whenever you're solving for an exponent, you take the log. And so this ends up being equal to n times the log of 1 minus p equal to log of 1 minus probability of frame error. And you can figure out the log of this value, the log of this value, and then just solve for n. All right, now just for the last bit of the tutorial, just a quick word about question 5. So I did have one student ask, you know, is there a better way than just completely brute forcing this question and writing all the possible combinations of bits? There is a slightly quicker way, and if you look at the solutions, you'll see the approach. It's you know, you can see the details in the solutions, but the idea is that we need to stuff the bits, or we need to perform bit stuffing if we have 3 ones in a row, right? And so the idea that I took in this question to make the solution a little bit simpler is that, you know, if we have 3 bits in a row, we don't really care what comes after it because we've had to stuff at least once. And so if we consider one, two, three, four, 5, if we consider a frame with 5 bits in it, if we have a 1, and a 1 occur right off the bat, then, we don't really care what occurs after it. And so the probability of this sequence occurring, if the probability of a 1 bit is equal to p, and the only reason why I set this equal to p is just so that we can, hopefully, it makes the equations a little bit easier to look at. If I set it equal to a half right off the bat, then there's just so many halves jumping around that it's sort of hard to follow. So the probability that this sequence occurs is equal to p times p times p. And then what do we put in for the probabilities of these last 2 bits? We don't care what they are. So they could be either a 0 or a 1. And the probability that a bit is equal to 0 or 1 is equal to 1, right? We're guaranteed to get one of those 2 results. And so the probabilities for those last terms are just equal to 1. The next sequence that we could have is our first bit happens to be a 0, followed by 3 1s, and then we don't care what comes after. And so the probability of this sequence is 1 minus p, and then we have 3 p's in a row. And then we don't care what this bit is, so that bit gets a probability of 1. And then the last sequence is when the 3 1s happen to occur at the end of the frame. So in order for exactly 3 bits to occur at the end of the frame, we have to have a 0 there, and we don't really care what came before. So we have 1 times 1 minus p times p times p times p. And so if you guys had done the brute force method and sort of added up all the individual terms, you'll find that your answer would be equal to the one that we did this way. This way is just a little bit of a shortcut.